recording as always, so you will be able to go through this recording after all. And I will show you my. So I will start with Turbine because my compressor project is downloading right now. And all of you have your finished projects, and we need to start the result menu in order to download a post processor of NCCFX, where we can post process our results. I mean, the procedure for compressor and for turbine, they will be absolutely the same. There is no difference. Maybe I will also show you the compressor, but in general, the steps are the same. Second. Some steps before we can start. So because we use turbomachinery mode for preparing our model, it was easier for us, less additional steps. The same way we can do here in post-processor. So you can see that there is a tab which is called Turbo. So we need to go there in Turbo menu, where we can use very special templates of ANSYS to post-process exactly a result of turbomachinery. But before we start, we need to initialize all our components. So you press this button, initialize all components, and we need some time to wait for the program to do the initialization. If everything is okay with your initialization process, you will have this blue tick near each component, but it is better to check whether everything went okay. So you need to double click on the first component. So for example, for me it's a stator component, and I need to check whether the hub region is correspond to the hub location of the model, shroud, blade, and so on. Especially this is important for periodics and for the inflow and outflow of our models. But normally when we use this turbo mode for preparing our model, there will be no problems during the compressor or turbine initialization. For example, if we prepare our model outside of CFX, for example, in other CFD program, and import the model to solve it in the CFX, then could be some problems, because at the step of preparing the model, the program gave the proper name of each region, and at the step of post-processing, it's easier for the program to recognize these regions. So just be sure that everything here is okay. And for the second component as well, so hub, shroud, blade, inflow, outflow, and periodics. And this green mesh also could be the criteria for you that initialization went wrong. So that means that having this green mesh means that the program was successful in the initialization of all the components. How it with your results? If is everything is okay with initialization?
Yes, everything looks good.
The same.
Okay, perfect.
Yes.
So, and now we can perform the analysis of the obtained results. First of all, we're interested into the blade-to-blade plots. So please press this button. What can we see here? Domains, of course, we are interested in all domains. Span 0.5, that means we're considering the middle section. The plot type first we will start with contour and, for example, static pressure, which is just pressure here, and press apply, and we will see the results. For your case, now you have only one blade of, for example, first component and only one blade for the second component. To do the multiplication of the components, you need to use this menu, Graphical Instancing, and for each domain, for example, R1 or S1, you can set up the desirable number of copies and press apply. I will open another result.
Sorry, can you return in the blade to blade menu?
Just a second.
Is it possible?
Of course, I would like to open better project with better results. So blade B2B, control, and press apply. So here it's the better results.
Okay.
So once again, span, it's about the location of this contour along the head of your blade. So 0.5 corresponds to the middle section. Then we're selecting contour, which is we can see the contours of some parameter. For variable, we will start with pressure, which is in this system means static pressure for us. And for number of copies, you use this menu. You just need to select R1, for example, press 3 and apply. S1, 2 and apply. So how can you perform the analysis of the obtained results? You know about the specific feature of operation of your turbo machinery type, and you can say using these contours whether your results adequate or not. So, for example, here static pressure is decreasing both in nozzle guide vane and in the rotor wheel. So we know that this is true. In turbine we have a decrease in this static pressure. Then we can say that everything is okay with these results. For compressor, it's obviously vice versa. Of course, we can check temperature, which is static temperature for us. If you would like to follow the results of total parameters in CFD post, then you need to use not, for example, total pressure, but total pressure in stationary frame. That means we consider in stationary frame when but when you select just total pressure, this will correspond to parameters with double index in this method. So for normal total parameters, you need to select this one, total pressure in stationary frame, for example. Once again, here, speaking about the results, we can see that, for example, in nozzle guide vane, there is no changing in total pressure, which is true because no work or no work extraction or submission in nozzle guide vane is occurred, so total pressure doesn't change here. Then we can see the decrease of total pressure in rotor wheel. And for compressor, the increase have to be in your compressor. what else we're interested in? Speaking about velocity, it's more interesting to follow Mach number. We press apply. When we select Mach number, we can see the absolute velocity in nozzle guide vane and relative velocity in rotor wheel. Once again, the results are correct because in nozzle guide vane there is an increase of absolute velocity and increase in rotor wheel of relative velocity. So once again, this confirms the adequacy and correctness of our results. How is with your results?
They're similar. Yes.
Okay, good. So also we can see how the flowing around our blades is going. To do this, we will use these two parameters, vector and stream. So let's start with vector. By vector, we can increase the size of the vector, if I'm not mistaken. So, and here, of course, we are interested in how the flowing is going around the blade. Here we can see that it's rather okay. The same situation with the rotor blade. And also the correctness can be followed by stream menu, the Streamlines. In general, we can see that the streamlines are rather smooth. That means that the profiled blade was done in a good way, and both for rotor and for stator. But for example, could be some flow separation if we check at the span somewhere near the shroud. So here you can see the flow separation at the suction side of the rotor blade.
And for me, the streamline is quite different because where are the two sections in the middle? My line is like a V, is not continuous smooth line.
Okay.
I will try to. Let's see.
Could you please send me the screen?
Yes.
So, and here this flow separation we also can see using the vector menus. All this information could be very useful for you to write a report if you need to do this, or maybe during your I don't know what in the end you will have some report or some writing work, finished report about your scientific investigation. So all these results could be inserted in your reports. For example, you can say that in general the profile blades are quite good, but still we can have some flow separation at the rotor blade closer to the shroud section, which can be caused by the interaction of the main flow with the flow in the radial gap, something like that.
Can you show again the flow separation, please, just to have a visual representation?
Here.
Oh yes, okay, perfect. Thank you.
In vector, you also can see this flow separation. It looks like.
For me, flow separation doesn't occur. So.
Yeah, me too. I don't have flow separation.
And even in the shroud section, there is no flow separation.
Yes.
Okay, could be, depends on the blade, and why not? The second, I will look at the screens.
My one is on the left, of course.
With your case, it's also like flow separation could be. I mean, it's not a big mistake, but this is some features of your flow inside the compressor. Also, could be some cases when you try to simulate not the design point, but how to explain that your point that you try to simulate is located not at the design point of the compressor characteristics, but maybe it's closer to the surge or to the stall mode, and this flow separation also could be because of these problems. I mean, this is not a big mistake. This is something of your flow.
But what about the change direction of the streamlines? Because they produce like a V, something similar.
You mean here?
No, after between there is the black line in vertical. Okay.
You mean this here?
Yes.
This.
Yeah. On the left, the lines are going down, and on the right, the line are going up. But the transition is very rigid, not smooth like yours.
For me, it's how to explain. This is because we and how to explain this because we considering this in different velocity, not velocity, like rotational frames. So if you select here, for example, so if you select here, for example, velocity in stationary frame for streamlines, which picture will you have for your compressor?
I will send you. Like this.
So this was a problem for you. You think that this is a mistake?
Yes. Yes.
You can see that when we select just velocity, in this case we consider for example, stationary component, stationary frame, for rotational component, rotational frame. So they could not be, this is not a mistake that they are not corresponding these lines, because when we select just velocity, we consider each component in each own frame. It's not
okay. Okay, I think now I understood, but I took that before the line have to change its direction, but okay, now I understood.
And when you select this one, velocity in stationary frame, that means we consider both components in the same frame, in the same coordinate system. In other words, it's not a mistake. What else can we see here? We can see the distribution of parameters along the path of the flow or meridional frame. Okay, so this is how the some parameter, for example, static pressure, is changing in the meridional section of your turbo machinery. Here's the picture. Sometimes because of different location of your components from the stage of preparing your model, could be not very correct representation of these meridional planes, so be careful. Check that, for example, in turbine you have exactly decrease of your parameter, for example, of the pressure, because I will show you some cases when students send me their reports about turbine. So, for example, here they performed this analysis with meridional section. This is about turbine, but you can see that in this case the meridional section is located not in the correct way, and here we can see the increase, which is not physical for the turbine,
Yes.
but in general the calculation is correct, because, for example, here everything is okay, here everything is okay, but because of the representation of the model, here there are some problems with the representation of the results. So be careful with this point.
Okay.
Okay.
Of course, we can judge about the correctness of our results using contours, vectors, and path lines, but also we need to be able to calculate some integral parameters of our turbo machinery. To do these calculators will be very useful for us, or function calculators. And I prepared for you the presentation with 2 new slides, and I will send this presentation after the lesson in the conversation. Of course, we are interested in the efficiency of turbo machinery, and I will give you the formulas how can we calculate the efficiency for both compressor and turbine. I believe you have these formulas from lectures.
Yes, we have.
I think so.
I will comment very fast on these formulas. Let's start with turbine. Turbine efficiency, it's a ratio of a specific work on turbine shaft to the ideal as entropic work. To calculate entropic work is very, very simple. K and R, you know these parameters, the gas constant and the adiabatic index. 0 and P0 and P2. So this information you can get from the calculator. So to do this, you need to go to the function and select mass flow oven. That means we will get the result averaged by the mass flow of the working fluid. Then you need to select the location. For example, we are interested in the total temperature at the inlet. So that means in the list of location you are selecting S1 inlet, and you need again to select not just total pressure but total pressure in stationary frame, and press calculate. Actually, these values also can be extracted from your initial data. And also, I would like to show you that like stationary components, there will be no difference between total temperature in stationary frame and just total temperature, because there is no relative motion in this component. So, and for pressure, it's the same. So you need total pressure at the inlet, and you need to calculate total pressure at the outlet. Here you can find the values. What else can we extract from the calculator? Here, using these parameters, we can calculate isentropic work. Then we need to calculate useful specific work on turbine shaft, which is the ratio of turbine power divided by the mass flow rate. Speaking about turbine power, we need to multiply torque by this ratio. P is understandable, N is the rotational speed, which is going from your initial data from your previous stage. To calculate torque, so you need to go to calculator once again. In function, you need to find the parameter torque. Then you need to think about the rotational axis. If I'm not mistaken, this is a second. If I'm not mistaken, the rotational axis for us was X, or was that? I have forgotten.
I think it's Z.
Z. Yeah. I think so. Yes.
For me, I
Yes.
don't know.
Rotational axis, yes.
So here, this information, of course, you can check from CFD preprocessor if you are not sure about the axis. But let's do this. No. Yes, I think it's Z. So yeah, you need to set up the proper rotational axis. I'm sorry, and for location, of course, you need to select R1 blade, because we are calculating the torque on the exactly on the blade. So we can calculate the value. Minus means the difference in the rotational direction and the coordinate system. It's not a mistake. But here is the value only for one blade. So to get the value of the torque, so you need to calculate the value you've found using CFD from calculators. You need to multiply this value by the number of rotor blades. Here we have this component, and also we need to calculate the mass flow rate. Also, this information can be found using calculators. Here in function, you need to select the parameter mass flow. And we need to select, it doesn't matter which, S1 inlet, for example, or R2 or R1 outlet. Minus means that the flow is going outside of our model. This is also not a problem. And you need also to multiply these values by the number of blades. So if we're speaking about S1 inlet, then we need to multiply this value by the number of nozzle guide blades. For the R1 outlet, obviously, you need to multiply by the number of rotor blades. So here in this formula, you have this information. So now we have all the necessary information to calculate the turbine efficiency, and also you can compare the results you've got from CFD calculation and the results you've got at the previous step for the just analytical formulas. So you can compare these values, not of course not only the efficiency, but the other values as well, like temperature, pressure in different sections, pressure ratio, and so on. And you can say what is the difference. between these results. So, any questions about post-processing turbine results?
No, it's clear.
It's clear.
No.
Do we need
So
to?
the mass flow should be, I mean, it should respect the continuity. So the mass
Yes.
flow at the inlet
Mhm.
should be the same as the outlet. If
Yes.
it's not so, there is a problem, right?
Yes. Right.
Okay. Okay.
So, of course, you need to multiply. First, you need to multiply these values by the number of blades.
For every blade, yes.
You need to compare these values, and if everything is okay with your calculation, these values will be very, very close.
Mm-hmm. Okay.
Because, for instance, for me, I at S1, starter 1 inlet, it's not the same value as a rotor blade inlet or mass flow.
After multiplication, you mean?
Yeah. No. Just yes, just raw value. So yes. My mistake.
Yes. In turbine, normally the number of rotor blades twice time bigger than the nozzle advance, and exactly you will get the same. Most likely you will have
Okay.
for your turbine. Do you need to cover a compressor in the same way, or it is clear for compressor guys how to post-process the results?
I think it's okay. It's just the parameters to use differently, but I think it's quite the same parameters. No?
Yes, just invert the R1 and S1.
Yes.
I mean, I also prepared the file for you for the efficiency calculation. So for efficiency, you can see that the ratio is vice versa. But the other formulas, they are exactly the same. So once again, T1 and P1, you need to calculate these values at the inlet of your model, P3 at the outlet of your model, torque, mass flow rate, and the other parameters, they will be calculated exactly in the same way. So for torque, do not forget to set up the proper rotational axis. And for location, do not forget to select the blade of your rotor wheel. For mass flow rate, of course, do not forget to multiply by the number of blades, rotor, and nozzle. I'm sorry, for the guide wheel correspondingly. So, it will be good. So I will send you these formulas, and I think this will be very good if you will prepare a very small report about this work. Or maybe in your final work you will have some chapter about CFD calculation. You can send to me and Mr. Baturin just this chapter from your final work. What is more convenient for you? For us, it's okay.
Okay.
Yes, okay. And just a question, is it better, for instance, for pressure to represent in vector or in streamlines? There is no incidence.
Just a second, once again. So you would like to...
Yes, for instance, when we want to show, I don't know, Mach number, for instance, is it better to show contour, vector, or stream?
For vector and for streamlines, you can select only velocity.
Yes, it's only velocity.
So for pressure, temperature, Mach number, you have the option only to show the contours. And for velocity, but I mean, Mach number, of course, it's the correlation with velocity. And vector and streamline also. So, I mean, the values will be the same, but using vectors and streamlines, you just can represent how flow is going around the blade, whether the flowing of your blades is okay, or do you have some separation. Actually, for example, even using Mach number or just velocity contours, you also can see some problems here. But with like streamlines and vectors, it's more represented to show the direction of the flow, how vectors is located here, or how the streaming of your flow is going. So I mean, they are about the same things, but in telling us in different ways.
Okay, perfect.
So any other questions?
No, it's okay.
No.
Everything looks clear here.
I don't think that this will take very long time for you to post-process the results, because it's quite understandable. If you have any questions during the post-processing your results, you can write me an email or via Skype. I will be happy to answer these questions. So yeah, and I believe that this is the finish of our CFD course. Thank you very much, guys. For me, it was very interesting. But it's all the time very good experience with foreign students to go through this course. It was very pleasant time for me and with you, especially because we like try another format of the lesson via Skype. It's again new. Thank you very much once again, and I hope that this course was useful for you and you will use this knowledge further, not only in education but in your maybe during your job and some research project and so on. Thank you very much.
Thanks to you for everything.
Thank you.
Thank you, Dario.
For the clear and for the lesson.
Yes. And yes, just a final question. How to understand and to know if the model is wrong? Because we don't need to make modification on blade and everything. We keep this model until the end or not, or we will have to change if some results are not good at all.
Of course, first you need to follow some basic principles like increasing or decreasing pressure and temperature and velocity. Usually the mistakes in changing of these parameters means not the problem in, for example, blade profile, but usually in the problems of your model. I mean, maybe you've selected the wrong rotational axis, or I don't know, you set up bad boundary conditions and so on. Then of course you need to follow the vectors and streamlines of your flow in your turbo machinery. If there are a lot of problems in the structure of the flow, like a lot of separations, or maybe you can see, just a second, I will show you. For example, here, for example, here we can definitely say that the flow is going in the right direction. It's going towards the leading cage, then trying to streamline the flow, but could be that the vectors is located not towards the blade, but for example in this direction, or I don't know, very what is how to say. So using this vector picture, you can say about the good inflow angles of your model. So if we can see this picture that everything is okay with your inlet angles, for example. Here, yeah, quite okay, but I think something can be improved. But in general, using streamlines, you can see that in general, streaming is going okay. So be careful with compressor blades, I mean rotor blades. So using vector picture, you once again can say that you've selected the proper alpha 1 angle during setting up your model.
Okay.
I think this is the second criteria for you. And the third one, of course, integral parameters. So, speaking about efficiency of your turbo machinery, we understand that, for example, if you get some unphysical values like greater than 1 or 100%, then something is wrong with your model. Or too low values of efficiency also could tell us about some problem in the flow inside turbo machinery that we need again go carefully through the flow structure. And also the criteria for you could be the comparing of CFD results and the results of your gas dynamic calculation. So it should be not very great difference between these values. I mean, using analytical formulas and CFD calculation.
Okay.
And then speaking about changing something, I don't know, because some of you, as far as I know, you're calculating the real machine, so the real compressor or turbine. In this case, we need to consider maybe we can improve the profiling of your blades, or maybe we need to change some boundary conditions. So I think this is a discussion for the next step when you first process.
Okay.
But in
Okay.
general, these are the criteria. So basic principles like streamline of your blades and integral current in comparison with gas dynamic operation.
Okay. Clear.
Yes.
Okay. If you will have questions after all, so write me an email or via Skype. So that's all.
Okay.
Okay.
Thank you very much, Daria. Thank
Yes.
you.
Yes.
It
Thank
was
you.
Thank
very
you.
useful, by the way, as you said,
It was my pleasure, and I hope that soon
for us too.
Yes.
will be stable in the world.
Thank you.
Yes, it was a pleasure. It was a pleasure. Anyway, in distance, but it was a pleasure too.
Thank you very much. Thank you very much. So have a nice day, and goodbye.
Yes.
Okay.
Goodbye. Thank
Yeah.
you.
Thank you.
Bye. Thank you.
Goodbye. Thank you.
Goodbye. Bye bye.
Bye.